Welcome to the Deep Dive. Today, we're embarking on a journey into the incredibly small. We're exploring the fundamental particles that make up pretty much everything around us, quarks. Our mission, and we're drawing heavily from Andrea Minini's excellent The Universe of Quarks, Tiny Builders of Matter, is really to unpack what these particles are. We'll look at their, well, truly strange properties and try to understand why they're so essential, why they're the building blocks of all matter. So, yeah, get ready to maybe rethink reality a bit.
It's fascinating because for a long time we thought protons and neutrons were it, the end of the line, indivisible. But quarks really blew that idea open. They showed us that even the core bits of atoms can be broken down further. They really are the tiniest building blocks we know of.
Okay, so let's start right there. What exactly are quarks? And who first even, cooked up the idea of these tiny things?
Well, quarks are fundamental particles, the smallest known constituents of matter. They combine to form larger particles, the most famous being protons and neutrons. The idea itself came from the American physicist Murray Gell-Mann back in 1960. He basically theorized that protons and neutrons weren't fundamental. And it didn't take too long, actually. Just 3 years later, 1963, the first experimental evidence popped up for the up and down quarks. So his idea got confirmed pretty quickly.
Wow, 1963. That's surprisingly recent, isn't it? Considering how fundamental they are. Now, you said they're inside protons and neutrons. Can we, ever find one just floating around by itself? Can you isolate a quark?
Ah, that's a great question, and it hits on something really key about quarks. The answer is no. You actually can't observe them in isolation. We only ever detect them when they're bound together inside other particles like those protons and neutrons you mentioned. They're perpetually confined.
Okay, perpetually confined. So what keeps them glued together so tightly then if you can't pull one out? Is it I don't know, cosmic superglue or something?
A slight chuckle, implied in tone. You could definitely think of it that way. It is like an incredibly strong superglue. It's called the strong interaction force. This is one of the fundamental forces of nature, and here's the really interesting part. The force actually gets stronger the further you try to pull the quarks apart.
Wait, stronger?
Yeah.
When you try to separate them? That seems counterintuitive.
It absolutely is. That's precisely why you can't isolate them. The energy required just keeps increasing. And it's the same fundamental force that also holds protons and neutrons together inside the nucleus of an atom.
That is wild, a force that pulls harder when you stretch it. So, okay, are all particles made of quarks then? Or is it just a specific club?
No, it's definitely a select group. Only certain families of elementary particles are made of quarks. We call these hadrons. Hadrons include baryons, that's things like protons, neutrons, but also others like lambda, sigma particles, and also mesons like pions and kaons. But other big families of particles like leptons, think electrons, neutrinos, muons, and the gauge bosons like photons or gluons, they do not contain quarks. They're fundamental in their own right.
All right, so hadrons have quarks. For those particles, how many quarks are we talking about? Is there a standard number?
Yeah, there are two main configurations. Some particles, the mesons, are made of two quarks, specifically a quark and an antiquark pair. Others, the baryons, are always made of three quarks. That's your proton and neutron category.
Three quarks. Okay. And I've definitely heard them described as having flavors, which, does that mean anything about taste? Seems unlikely.
Tone implies amusement. Yeah, not quite. Flavor is just a name physicists came up with. It's a label for a specific quantum property that distinguishes the types of quarks. Nothing to do with taste. There are 6 types, 6 flavors in total. Up, down, strange, charm, beauty, which is sometimes called bottom and top. They're also grouped into 3 generations. The first generation is just the up and down quarks, and those are the ones that make up protons and neutrons, so they're the most common by far in everyday matter.
Right, up and down are the workhorses. Now, this is where things get even stranger, right? Quarks have some really non-intuitive characteristics, like their electric charge.
You absolutely do. That's probably one of the weirdest things about them. Each quark carries a fractional electric charge. It's either positive or negative 2/3 or positive or negative 1/3 of the elementary charge, the charge of a single electron or proton.
But hang on, fractional charges? How does that work? Because protons have a charge of exactly +1, and neutrons are neutral, 0. How do fractional charges add up to whole numbers?
It's actually quite neat how it works out. The combination of the fractional charges within a hadron always sums up to an integer 0 plus 1 or minus 1. So take a neutron, it's neutral, right? That's because it has 2 down quarks, each with a charge of minus 1/3, and 1 up quark with a charge of plus 2/3. So minus a third, plus 2/3 equals 0. And a proton, it's got a +1 charge. That's 2 up quarks, so plus 2/3 each, and 1 down quark at minus 1/3. Add those up, 2/3 plus 2/3 minus 1/3 equals +1. It just works.
Okay, the math checks out. That's pretty elegant, actually.
Hmm.
And beyond charge, they also have properties called spin and even color, right? What's that about?
Yes, exactly. Quarks have what's called half-integer spin. Spin is an intrinsic quantum property, kind of like angular momentum, almost like they're perpetually spinning, though that's just an analogy. It affects their magnetic properties. And then there's color. Quarks are assigned one of three colors: red, green, or blue. Now, crucially, these are not real colors you could see.
Right, just labels then.
Exactly. They're just labels for another kind of charge, often called color charge. It's part of the theory called quantum chromodynamics, or QCD, which describes the strong force.
So why invent color? What does it do?
It's actually fundamental to making the theory work. It solves a potential problem with something called the Pauli exclusion principle. That principle basically says you can't have two identical fundamental particles in the exact same quantum state in the same place. When physicists looked at particles made of three identical quarks, like maybe three up quarks, it looked like it might violate that principle. Introducing color as another quantum number, red, green, or blue, means that even if all other properties are the same, the three quarks will always differ in their color, satisfying the Pauli principle. And, just to add, for every quark flavor and color, there's a corresponding antiquark with opposite charge and an anticolor, like anti-red, anti-green, anti-blue.
Wow. Okay, so we've gone from thinking protons and neutrons were the end of the road down to these tiny fractionally charged colored things that have flavors and are permanently stuck together by a force that gets stronger when you pull. It really does shift how you picture reality.
It absolutely does. Delving into quarks reveals just how fundamentally strange, but also how elegant the universe is at its very smallest scales. It's a reminder that reality is often deeply counterintuitive compared to our everyday experience.
And that leaves a really interesting question for you listening at home. What does it truly mean for our understanding of reality that the most basic pieces of matter we know have these bizarre properties like color and fractional charge? How much more could be hidden down there in the fabric of matter that we haven't even begun to grasp yet? Something to think about until our next deep dive.